เย็นทำไมครับพี่ทำไมครับพี่เสียใจว่าไม่ได้ครับใครเอาผลงานไปไหนแล้วและไม่เกิดและไม่เกิดกันเริ่มติ๊กต็อกแล้วเฮ้ยทำไมไอ้เหี้ยทำไมโอ้ยมันคือแฟนนะโอ้ย เฮ้ยคนข้ามมาเลยเฮ้ยเกมข่าวมาต่อมาครับเฮ้ยเยโร่
Test 1, 2, 3. Okay. Good afternoon, everyone. Welcome you to SCI33206. เขาแจ้งมานะครับว่าวันพุธหน้าตัดคาบเรียนที่10เราถึงคาบเรียนที่10กันหรือเปล่าครับ
วันไหนครับ
วันพุธครับ
วันพุธเหรอ
พุธเรามีถึงวันที่10คาบเรียนที่10กันหรือเปล่าเอ่ย
วันอังคารอยู่เนี่ยครับมีครับแต่ไม่ได้
เดี๋ยวคนละเรื่องวันพุธครับวันพุธอะไรนะไม่ถึงใช่ป่ะแล้วไม่เกี่ยวข้องนะโอเคได้ครับอันนี้ next one เราไม่มีอันนี้นะอันนี้605มีประมาณนี้นะครับที่วุ่นนะว่าจะต้องเขาเรียกว่าอะไรพวกลาครับที่สุดแล้วก็ขอทำความเข้าใจกับคุณอีกนิดนึงนะครับเขามีบอกว่าจะนัดเรียนเพิ่มอะไรนะชดเชยวันพฤหัสใช่ไหมครับพฤหัสแล้วเขาจะคุณไม่ต้องเรียนรดแล้วใช่ไหมครับไม่มีแล้วใช่ไหมโอเคIt's going to be somehow like this นะที่ลาก็คือมีวิบูลย์นะครับ1คนนะครับวิบูลย์เนาะวิบูลย์ออลิฟเหมือนเดิมนะครับแล้วก็ next person ศิลภพนะครับที่ไม่อยู่นะไปธุระครอบครัวครับก็ปัณฑรคนไหนนามือครับนี่เหมือนกันหมายเลข24นะครับธนทรไม่ใช่ปัณฑรแล้วก็ณธนนท์นะที่ไปแซฟเหมือนเดิมแซฟแล้วก็สหรัฐไม่อยู่นะสหรัฐยังไปแอคอยู่นะเลข11alright and ตัชดลนะตัชดลหมายเลข27นะครับ27แล้วก็ทันวินนะครับโอ้โหภารกิจสำคัญทันวินคุณลาไปมอบดอกกุหลาบให้ผู้หญิงหรือเปล่าเนี่ยภารกิจสำคัญเนี่ยหมดแล้วนะครับ ที่ลาไว้นะมีคนอื่นอีกไหมเอ่ย sorry กูพละกลับใจไม่มีอีกแล้วนะครับโอเคคนแรกนะครับคณาวุฒินะครับชัยกรนะครับขอโทษครับแอร์คุณแรงครับ ถัดไปก็นัทวัฒน์นะครับ แล้วก็ธนากรนะครับ แล้วก็ทัศน์นะครับ แล้วก็อนิวัฒน์นะครับ โลลวีนะครับ แล้วก็สหรัฐนะครับสหรัฐไม่อยู่เนาะสบัตครับ จีโน่อยู่นี่แดนฟ้าอยู่นู่นนะครับฮะชัยกรเดนิสบุญยวีครับ อยู่ไหนไอเห็นหน้าหน่อยภูมินันท์ครับ กันเอกหายไปไหน กันเอกปล่อยว่างนะครับกริดครับกริดเคถ้ากริดครับถ้ากริดฮัลโหลปล่อยว่างประธรรมกริดจีโอเคเยี่ยมณฤทธิ์กสิเดชครับกันเอกภูเมศครับหมดแล้วนะครับหมดแล้วนะนอกนั้นคือลางจริงอ่ะไม่เหลือใครหรอกเดี๋ยวผมขอตัวไปเซ็นเอกสารที่ e-plus แป๊บนึงครับสบายครับเดี๋ยวผมมาครับ
Oh my god! Oh my god! Yes, wait, oh my god, you fucking cooked him! I fucking cooked him, bro! ไม่ได้ถาม As what the mask is,ฟังเวียนจริงอ่ะฟังเวียนบอกเดี๋ยวนี้กูโดนทำร้ายนะครับแม่นี่ทั้งหมดอ้วนไม่มีการฆ่าตัวตายเป็นการที่จะได้สองห้าสี่สามเอาทุกฝ่ายที่เราจะเห็นในหลักฐานที่เชื่อว่าคือแบบแต่มันก็จะคนเลยเกิดมาบาดใหญ่ตัวสมมติเราคนใช่ไหมที่เราใช้ที่ของโดนหรือโดนฟังแค่สองทุกอย่างนะครับทำอะไรแล้วตั้งหลักตั้งหลักแล้วผมเอาได้ไหมล่ะแต่ว่ามันต้องแล้วก็ซื้อมาเคยเห็นว่าแบบบางทีมันมีคลิปบอกว่าคนที่นั่นก็ทำได้ดีทำตายมีรูปอะไรแบบทำซื้อไม่รู้ใช่ไหมรูปแบบยังไงไม่เจ๊สนใจก็คิดว่าจะเป็นอะไรมึงคิดว่ามึงโดนชนต่างโลกต่างโลกเป็นต่างโลกเป็นสีอาจจะไปดูบรรยากาศอะไรกันนะยืนอยู่หลังอะไรเที่ยวแตกมีลาวมีพราวว้าวคิวแรกนี่ว่าอะไรเป็นคนมีชีวิตต่อไม่เข้าใจว่าลาวมันจะเป็นคำตอบที่แบบผู้ใหญ่ทำ10%มันมีหลายอย่างมีเราควรไม่ใช่แค่อะไรก็อย่างแต่จริงๆเราเรื่องแม่เลยเรื่องแม่ดูแม่ไม่โกงแค่คือสอนแต่บางเรื่องโกง
ว่ามีไททานิกได้ด้วยนะครับสมัยก่อนคุณเกิดทันเหรอเรื่องนี้แล้วสมัยผมอยู่ปริญญาตรีนี่มันหนังโรแมนติกอะไรเขาเลยมากเลยนะโรแมนติกปนเศร้านะนี่ข้างข่าวขโมยกินกล้วยหนีมาไททานิกแล้วนะครับตอนนี้นะครับเพื่อนๆก็ทนฟังไปนะครับโอเคมาก
ไม่แต่มันเล่นเช้าแข่งไม่ได้มันอีบอกว่ามันกดครึ่งหนึ่งได้จริงเหรอแต่ว่ามันไม่บาลานซ์ขนาดนั้นไม่ได้ให้คุณบอกกันได้ไม่ได้อะไรเนี่ยพี่ซิ
คุยมันโน้ตเต็มใช่ไหมครับโน้ตทีละตัวแล้วถ้ามันชาร์ปมันแฟตนี่ทำไงอ่ะ
เขาบอกว่าคนครึ่งนิ้วแต่แบบมันไม่
มันก็ไม่เป๊ะใช่ป่ะแบบว่ากีตาร์มันยังมีดันสายอะไรช่วยโอเคOkay, good afternoon, everyone. Let's really start our lecture. So many people talk to me about everything in A+. Okay, okay, you know there are three quantum numbers, right? The first one is the principal quantum number, and the second one is orbital quantum number, and the third one is orbital magnetic quantum number. So that those seems to be sufficient for satisfying the Schrödinger's wave equation. But in fact, this is what we have already seen, right? And the way to represent it in a specific society, okay, in quantum mechanics society, they would not use the straightforward number 1, 2, 3, 4, 5, 6 like this. Okay, they have their own specific symbols. Those are called K, L, M, N, O, P. This is the shell symbol. Okay, they have also the specific word, which is called shell symbol. And L, which is the second right, orbital quantum number, has its own specific symbol, which is called subshell. Okay, this is big one shell, and another one that has a variation. Okay, another one which is the variation of the former one is called subshell. Of course, the shell would be represented by the capitalized symbols or alphabets, and the subshell would involve only small font of the English letters. Of course, the arrow starts from 0, 1, 2, 3, 4, 5, and you can see that here we have a shell symbol from K, L, M, N, O, P, and here is S, P, D, D, F. Okay, S, P, D, F. Okay. We don't have the letter E in the subshell symbol. Do you know the reason why? Because E is used to represent the electron charge, right? So we cannot use E in the fourth subshell symbol. Okay, we have to skip the letter E and we move to the next alphabet, which is alphabet F, and so on, right? G, H. And if you have more, you can go further. Well, those three quantum numbers seems to be sufficient, right? But in fact, the physicists made the experiment and they found something that is quite special, and it doesn't go along with the theory that we have usually in the Schrödinger's wave equation result. Okay, the energy of the electron is slightly modified when atom is immersed in a magnetic field. So if you put an atom in a magnetic field, you're going to have a split of the energy level For example, if you have low magnetic field, low intensity of the magnetic field, the energy level is going to be seen as a single line like this. But if you have the moderate level of the magnetic field, this orbital energy would be split into two levels like this. And if you have even stronger magnetic field with more intensity, you are going to have a clear split between two energy levels like this. But how did the physicists notify there is split? Because they observed it from the spectrum of the light, okay, and the light that is used to detect this separation of the energy level is the yellow light like this. Okay, it's made from the sodium lamp. Okay, you have the coil, copper coil, something like that, and you fill that bulb in the lamp, with the sodium, and then you use the sodium as the coil, right? And then no, sodium is used as the gas inside that lamp. And once the heat is quite large, it's going to emit the photon like this, and you observe it from different levels of electromagnetic field strength. Yeah, you are going to see the split of the electromagnetic field like this. When external magnetic field are present, an individual spectral line in A is split into solar lines in B. Okay, here you have three lines, and the actual measurement is like this. If you have the yellow light from the sodium lamp like this, there is a splitting of emission of lights of atomic spectra. Well, it's 3p1 half and 3p 3 half. Well, you get the energy difference of 0.0021 electron volt between them. And the emitted photon will be also different in terms of wavelength, like 589 and 589.6 nanometer like this. And the difference of the wavelength is around 0.597 nanometer. Well, you would have approximation like 0.6 nanometer, okay, which is the approximate version of this value. The shell energy level is minus 5.14, and the big shell will be minus 3.03, but this will be split by 0.021 electron volt. So what is 3s1 by 2? 3s1 by 2 means is this one, okay. 3s, okay, 3s 1 by 2. By using the high resolution spectrometers, so you need to have a high precision measurement device, which is called spectrometers. It is found that the lamp using sodium vapor exhibit two close yellow frequencies, whose wavelength are 589 and 589.6 nanometer like this. These two distinct frequencies are known as phi structure. The idea of electron spin was widely accepted as the one that was suggested by Georg Uhlenbeck and Samuel Goldschmidt. but it was actually proposed by Ralph Kronig during his PhD in January 1925 at Columbia University. This effect was explained by the famous Austrian physicist whose name is Wolfgang Pauli. To describe the atomic energy levels, he proposed a fourth quantum number, which is called the spin magnetic quantum number, or is denoted by M, small m with the capital S. The spin number ms is not any feature in the solution of the Schrödinger's wave equation, but naturally arises in the equation derived from Paul Dirac in 1927. Okay, yeah, that's the development in physics. In order to explain why we have two separated light frequencies like this, light wavelengths. Okay, and it can be explained like this. If you have the nucleus of an atom, electron would move around the nucleus, right? And we assume that the electron seems to turn around, okay, according to the right-hand rule like this, and it's called spin up, because your thumb direction is pointing up like this, and your four fingers represent the direction of the movement of the electron, but actually the electron doesn't move. Okay, that's the idea of the spin up. With the spin up configuration, we are going to assign ms equal to 1 by 2. Okay, and if we go to the next possibility, which is a spin down. When electron move around the nucleus, we assume that electron turns around in the clockwise direction. If you consider the top view above the electron motion, and according to the right-hand rule, this is the rotation direction of the electron. You're going to have a spin down. Spin up or spin down would better explain the magnetic pole that can be created by the electron. Energy of the electron is slightly different for the two spin directions. This energy difference accounts for sodium doublet. Okay, so sodium double waves. This new quantum number doubles the number of allowed states that are previously specified by three quantum numbers, such as principal quantum number and L, right, which is the orbital quantum number, and ML, which is the orbital magnetic quantum number. So we have 2 times of the whole amount. And if you want to completely determine the number of states that can exist for an atom, okay, we are going to consider the first example, which is taken from the book number 1 in example 28.3. Okay, let's consider a hydrogen atom. Determine the number of states with a unique set of values for L, ML, MS, for M equal to 2. Of course, when your when your n is equal to 2, you will have this one. Okay, my God, it was just deleted. when you are n equal to 2, right? You would have three cases, right? N equal to 0, n equal to 1, and n equal to 2, right? When your n is equal to 0, is going to, you would have no, you would have only n equal to 1 and n equal to 2. This is L equal to 0, ML is also 0. And here you have L equal to 1, L equal to 2. Oh, sorry, L is 0 and L is 1. Here you have ML equal to 0. And ML equal to minus 1, ML 0, ML equal to 1. All right? If you cover the possibilities, okay, you have 1, 2, 3, 4, 5 choices. And the total number would be, here you have ms equal to minus 1 by 2, ms equal to 1 by 2. You have 8. Why? Oh, no. This is n equal to 1. Here you would have ms equal to minus 1 by 2, ms equal to 1 by 2, and also here ms equal to 1 by minus 1 by 2, ms equal to minus 1 by 2, and also here, and also there, right? If you count it 1, 2, 3, 4, 5, 6, 7, 8, you would have 8 quantum states. That's the number 8. Okay. Let's consider a hydrogen atom determine the number of states with a unique set of values for L, ML, MS when n is equal to 3. So when your n is 3, when you are n, sorry. Your principal quantum number is number 3. You would have L equal to 0, right? And L equal to 1, and L equal to 2. Here you would have ML as 0 only. And here you would have ML as minus 1, ML as 0, ML as number 1, and you would have 5 in this case. Okay, here you would have ML as minus 2 and ML as minus 1, ML is 0, ML is plus 1, ML is number 2. So, and furthermore, you're going to have MS equal to minus 1, or minus 1 by 2, ms is plus 1 by 2, and so on. Okay. So if you count the number of possible quantum states, you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the number of quantum state is of quantum states is 18. Okay, as you count the possible combination of L, ML, N, L, ML, MS. Okay, that's 18. Like this. Let's check whether we are correct or not. Okay, we have 18 quantum states. Okay, that's the reason why. Is the electron spin realistic? This is one of the question. In order to get the answer to this, we're going to need to consider the moment of inertia and the spinning speed of the electron. If the speed is beyond the light, okay, it's important. We're going to assume that it's impossible. It doesn't occur in reality. Let's consider the spinning speed of the electron, okay, which is actually the tangential speed. As soon as the electron has the shape similar to the football or the sphere. Okay, if you stay on the skin of the football or the electron, your speed, your tangential speed, your movement speed should not be greater than the speed of the light, which is approximately 3 times 10 to 8 meters per second. Okay, you cannot be beyond that value. And the tangential speed can be determined from the angular velocity of the electron, how fast it turns around in radian per second, and the radius of the electron. Okay, if the electron has the big radius, your speed is going to be also larger. Okay, it's proportional. It's directly proportional to the radius of the electron. But the radius of the electron is a fixed value, it's a constant. And okay, now we are going to find the possible value of the angular speed omega. Let's recall the moment of the inertia of a sphere, which can be found as I sphere equal to 2 by 5 mr squared. M is the mass of the sphere and I is the radius of the sphere, of anything that has the spherical shape. And it is well known that the angular momentum of any object is the product of the moment of the initial I and the angular speed omega. And the angular momentum of the electron is subject to 1/2 h/, which is the reduced Planck constant. So we can equalize those quantities. The angular momentum, which is derived from 2 by 5 mr squared in 2 by 5 mr squared and omega. It should be equal to 1/2 of the 1/2 the reduced Planck constant. So this is the angular momentum of the spherical shape, right? mr squared. Yeah, this is I 2 by 5 mr squared times omega. The product between I and omega, that's the angular momentum. So we have the left hand side here. And now you substitute Vt, which is the omega times Re. Omega is Vt by R, right? So we would have Vt by R. Vt by R, and you have only R here. And now you solve this equation for Vt, you will get the speed, which is 513.15 times 10 to 8. You can see that this value is greater than the speed of the light. If you stay on the skin of the electron, you are going to have this value as your movement speed. And this is beyond the speed of the light. Doesn't occur. Okay? It's not acceptable. It cannot exist. So the electron's spin is actually impossible. From this calculation, okay, we get a conclusion that the electron cannot spin in reality. Okay, an important notice is that the electron doesn't physical spin, okay, and whereas the electron spin is a pure quantum effect that gives the electron an angular momentum, as if it were physical spinning. Spin is an intrinsic form of the angular momentum. The Pauli exclusion principle states that no two electrons in an atom can ever have the same set of values for the set of quantum numbers such as in L, ML, and MS. Two electrons cannot share the same quantum state. Okay, this is the principle from Wolfgang Pauli, an Austrian physicist. And here is the number of electrons, and you can count it. Okay, for example, the first shell m equal to 1. You are going to have only single subshell, which is L equal to 0. And if you go further, you would have only number of electrons in fewer subshell. You would have only 2. And number of electrons in a few shells would be number 2. When you are n equal to 2, you would have L equal to 0 and L equal to 1. And each of these would provide you 2 electrons, right? ML equal to 0, but you should take into account the possible 2 values of speed number, -1/2 and +1/2. And for L equal to 1, you would have 3 pairs, right? So it's going to be number 6. When you combine this, you would get 8, okay, number of electrons in the filled shell. When your n is equal to 3, you would get 18. So what is, when your n equal to 4, what is the expression for this? The way to get the number of allowed electrons would be in this example, so you get 2n squared. It depends only on n. When your n is 1, so you will get 2. When your n is 3, you will get 18. When your n is 2, you get number 8. When your n is 3, you will get 18. When your n is 4, you will get 16 times 2, which is 32. Okay, spectroscopic notation. When your n is 1, you will get L equal to 0, ML is equal to, so you would get 1s. But there would be 2 states, right? Spin up and spin down state. Okay, when your n is equal to 0, you would have L equal to 0 and ML also 0. This one would be called 2s. Okay, there would be two possible electrons residing in this shell. And วันนี้ดีมากครับ When your n is 2, another possibility for the L is L equal to 1. You will have 3 pairs, right? Minus 1, 0, 1. This is called 2p, okay? Because here is when your n is equal to 2, it's going to be called when your n is equal to 2, you will say this is L, and the sub symbol will be when your L is 1, it's going to be say P. Okay, it's called 2p, but we have 3 pairs, you will get 6, and the combination of these will be 8. When your small n is 3, it's going to be called shell M. You would have 0, minus 1, 0, 1, minus 2, minus 1, 0, 1, 2. Because this is M, right? So it will be called 3, right? And the small letter would be SPD, okay? And you have here 6, 4, and 5, 9 pairs that will return 18 quantum state to the shell M. Regarding the next one, when your small n is 4, okay, you would have the same thing, the same way, right? 0, minus 1, 0, 1, minus 2, minus 1, 0, 1, 2. Minus 3, minus 2, minus 1, 0, 1, 2, 3. And when you count, you would have the first pair, number 2, the 3 pairs leading to 6 quantum state, 5 pairs leading to 10 quantum state, and 7 pairs leading to 14 quantum state. If you count the whole number here, which is 8, 10, 18, and 14, that will be 32. Okay, that's the shell N. This is shell N, okay, which is small n equal to 4. So these are quantum state of electrons in the first 4 subshells. So you may be wondering, what is the name for each subshell? Why they use SPDF? I try to browse the information. It's found that S means sharp, P means principal, D means diffuse, and F is fundamental. So the number of electrons allowed in subshells and shells would be according to this table. When your n is 1, shell number is 1, subshell name will be 1, okay, 1 is 2, okay, because you would have 2 electrons. You would have 2 possible electrons to stay. And n equal to 2, you're going to get 2s1 and 2p6. Okay, because your L could be 0, your L could be 1, which leads to M equal to 0, ML equal to 0, ML equal to minus 1, 0, 1. And times 2, you get the 6 quantum state. When you combine this, you will get 8 electrons. And for the third shell, you would have 3S2, right? 3S2, 3P6, 3D10. Okay, because this is 5, right? So -2, -1, 0, 1, 2. You have 5 pairs. 5 pairs times 2, 5 times 2 will be the number of possible quantum states. So you get number 10. 2, 6, 10, that will correspond to 18. When your shell number n is 4, you would start with everything as 4. Okay? 4s2, 4p6, 4d10, and 4f14. Okay, when you count all of these, you get 18, 10, or 18, 8, 10, 18, and 14 would be 32. For the bigger shell like number 5, you would have 5s2, 5p6, 5d10, 5f4, 5d18, when the number of electrons is 50. And for the biggest one, shell number 6, you would get the same way, 6s2, 6p6, 6d10, 6f14, 6d18, and 6h22. And if you count it, this 18, 32, 50, and 72. Okay. So now we look at how we get the formula to n squared. You would start with number 2, right, which is the L equal to 0 for the same orbital number. And you get L equal to 0, L equal to 1, L equal to 0, L equal to 1, and L equal to 2, and so on. Okay. Here you would get the summation. Okay, we have the share number, right, which is number 2. We moved L to we moved them to be there. Of course, the number of possible subsets will be 2L plus 1. If your L is 0, you would get only the 1. If your L is 1, you would get 3, which is 6. Okay. And we can separate the summation to each term, okay, in order to determine the closed form for the solution. Well, 2 can move in front of the sigma sign. L will be the result behind the sigma sign, the summation sign. And number 1 would stay also behind the summation. Summation of L equal to 0 until n minus 1. So this is n, right? This is n minus 1 plus n 1/2, and there is still number 2. You can cancel it, and what the remaining will be 2n squared, like this. Now let's talk about how we allocate the electron. How we allocate the electron onto this onto the shell, subshell in microscopic society. You start with 1s, and then you return to 2s, and then 2p. Okay, you have to go from top to down, right? 2p, and then 3s, and then 3p6, I think, yeah, 3p6, and then 4s10, right? 4s10, 14, 15, 14, right? You get 3D, 3d6, 4p2, and 5s10. When you start with 4D and so on, okay, along this zigzag diagram. This is called outbound principle. Okay, alpha principle. I don't understand why they call alpha. I think it's derived from. It's not the physics name. It is derived from how we construct or allocate electron around the nucleus like this. Another figure is that you can see when your n is equal to 1, you will have only a single. When your n is equal to 2, you get the split of the energy, right? N equal to 3, you have 3 splits. N equal to 4, you have 5 splits. 1, 2, 3, 4. N equal to 5, you would have more than that. 1, 2, 3, 4. N equal to 6, 7, you get here. 1, 2. The Pauli general exclusion principle states that no two fermions. Can you remember fermion? Fermion is the particle inside the left part of the elementary particle physics. Where is that? Here. This is fermion. Okay. Of course, fermion includes quarks and lepton. And electron is a kind of lepton. The former Pauli principle states that two electrons cannot share the same quantum state. But this is not, in fact, it's not only electron, but also other particles, like everything here in this table, which is called fermion. Okay. That's the Pauli exclusion, general exclusion principle. No two fermions or any particles with the spin number 1, 1/2, 3/2 can be in the same quantum state. The wave equation, which is phi depending on x, y, z, and t for the particle, contains all the information that can be known about the dynamic state of that particle. The wave function, psi, x, y, z, and t, is related to the probability of finding the particle in each of various regions. So we cannot know the exact position of the electron inside the atom. Okay, at the moment, maybe in your future, okay, when you live longer, when you can live here longer, human may be possible to determine the exact position of the electron, but right now they can only use the wave function that shows the probability of detection or finding in the location close to the nucleus. If the particle has a charge, the wave function can be used to find the charge density also at any point in space. The wave function can be used to find the average position of the particle. Okay, you just take the integration. Okay, and the average velocity, of course, it depends on the speed. Dynamic quantities such as momentum and energy, you can find all of these. And here is the figure of probability density function for the spherical symmetry, 1s, 2s, and 3s. 1s would be really at the beginning. 2s, okay, would be concentrated or also at the would concentrate also at the center and also the ring part like this. And when you are S is 3, 3s means you have three donuts. Okay. Three circles like this. The blue one will represent the property that you can find electron there. But that's concurrency with 100%. Now let's talk about Schrödinger's equation. As it is called, it was developed by Erwin Schrödinger in 1887 until 1961. But he developed this one in 1926. In Schrödinger principle, we can set up a Schrödinger's equation for any given physical situation. The wave functions that are solutions of this equation represent various possible physical states of the system. For an electron in hydrogen atom in a state with energy En and quantum number n, our acceptable solution of the Schrödinger's equation exists only when the magnitude L of the vector angular momentum is equal to L equal to R square root YL and L plus 1 times H slash, which is the reduced Planck constant. Okay, for L at 0, 1, 2, 3 until n minus 1. This is the magnitude of the vector angular momentum. The angular momentum magnitude along the z-axis can be only Ls is ml times h, okay, which is 0 plus minus 1, so on. The magnitude and the components of the angular momentums are shown in this figure. Okay, L equal to 0, that would be like this. You would have this is L equal to 2, and you can have many value of Lz. That's the angular momentum along the z-axis. Consider a hydrogen atom. This is the 3D. Okay, from the side view, this is from the top view. Consider a hydrogen atom in a state with n equal to 4. Find the expressions for the largest magnitude L of angular momentum, the largest positive value Lz, okay, the angular momentum along the z-axis. Corresponding values of the quantum number L and ml. Find the corresponding quantum state for the smallest angle that angular momentum vector can make with the positive z-axis. Let's consider the first one, largest magnitude L of angular momentum. Of course, L is square root L times L plus 1, right? Like this. But the maximum value should be observed or investigated in our case. If you want to maximize, you have to change L, which small l could satisfy this equation. Well, the highest one would be L equal to 3 and L. When your L is equal to 3 times 4 will be 12. And square root of 12 is around like this. Okay, we didn't use the exact calculation. But the reduced Planck constant could be substituted, and that's 1.05 times 10 to the negative 34. After the calculation with the square root of 12, you're going to get 3.65, 10 to the negative 34 to second. When your n is equal to 4, the largest positive area set would be max mLh, m equal to 0 plus 1 plus 4 minus 1. And you can substitute 1.05 into this expression to get 3.16 times 10 to the negative 34. You may ask why it's quite low, right? 10 to negative 34. Because this is the result for a single electron only. Okay, for a single electron only. Here's the max, right? The maximum value. So it's going to be 0 until 4 minus 1. 4 minus 1 number 3. So the maximum value would be 3h, right? 3h slash means you have to multiply it by 1.05 times 10 to the 34. You're going to get 3.165. Yeah, 16. This is 3.6. Angular momentum at any circle level, and this is the angular momentum along the z-axis. And the smallest angle that the angular momentum and the angular momentum vector can make with the positive z-axis is given by, you have to make the arc cross between RZ and L, common L. 3h slash and square root 12h slash, so it's going to be square root 3 by 2. That's easily equal to 30 degrees. And that's it for this chapter ครับเราจบบทที่ 6 นะครับ Atomic Physics เรียบร้อยนะครับ ก็เดี๋ยวว่ากันนะครับ ในบทถัดไปรู้สึกคอร์สศิริวัตรว่าไง Atomic Physics. Okay. The next 4 semester would be, the next 4 term would be experimental or something, experience or something like that. Nuclear physics and particle physics. Past attendance 10. It's 10. Next one will be laboratory. I'm going to find something for you to do the laboratory. Next one is
เดี๋ยวเขาจะส่งจดหมายมาให้ว่าไปหาแม่ดูหนังโอ้ยดูเด็กแปลก
นี่โคตรเก่งเลยแต่ไม่ใช่ครับเก่งของแบบที่ว่าหัวแตกตายเนี่ยครับผมใส่อายุจริงใส่ชื่อจริงว่าใส่ไม่ได้วายหรอต้องชื่อหนังฟูต้องใส่เขาบอกว่าไม่กลับบ้านอยู่ทำไมมีอะไรขึ้นกับวิ่งต่อน้ำมีรูปแบบผมก็ชีวิตมีรูปแบบว่าสมัยดูสมัยกับผมเลยสมัยกับผมอีเมลก็อยู่คุณทำงานคุณเลยคอมเมนต์เนี่ยโค้ชบอกสวัสดีครับผมธนาคารกวัฒน์อยู่ในโปรแกรมที่อะไรอายุ17 ปีเป็นผู้ชายเป็นพิการนะ
The time is so I need to go away ครับเวลาหมดแล้วนะครับผมต้องย้ายไปห้องนู้นนะครับได้ขนไม่ได้เลยครับ please.
How are they in your class? I try to do something, but they are not interested.
Yeah. The
Is that the same with you?
Yeah, the same.
See, on that book, there are videos to watch and analyze the video. I put the video, they just not bother. They just play the computer game. I don't know what to do.
Yeah. Just leave it like that because
Because, if I
this.
shout at them, they say, teacher, we have already got our universities.
Yeah.
So I don't know what to do with them.
Especially M605, right?
Yes.
Yeah, the same happened to me. Yeah. Before, if I didn't hear what you say, I would expect that they are boring because this is physics is too difficult, but it's not. As I
You know
hear
what I
from
did now? Because I gave them worksheets to do English for communication.
yeah.
And I told them to present. I
Yeah.
make them watch a video
Yeah.
and make them criticize the video. So at
Yeah.
least that's interesting. They're just not bothered about it. So I said, let me ask you because I'm close to you. I said, you having the same problem?
Yeah, the same problem. But I didn't assign any work to them because I deliver only the theory, the explanation. What I expect they should ask. You don't need create. Sorry, but that's happened the same. You can say that. No problem. You can tell me anything, but I have never get this experience before with M605.
The groups before this, were very nice.
Well,
It's my
yeah.
fourth group, okay?
Yeah.
The first
Last
second,
year.
very good boys.
Last year or 2 years ago.
Very good.
Yeah.
They used to sit down and listen to me, like
Yeah.
I used to tell them something. These groups, I don't know
Maybe
what to do.
maybe this is due to the quality. In the last few years, we didn't have so many students like this. We have something less than 30, but right now, it's almost 30 or plus. Sometimes we have only
24.
20, 24,
Yes.
but because this is the policy of the school, they want to get the numbers, maybe something like that. So they didn't have enough
Quality.
qualities for the student.
Because
That's why.
teacher, to tell you very frankly, before, like when I used to be not here,
Yeah.
and I knew this Wangula, it was the top 5 school,
Yeah.
and I
That's
had an
true.
impression about the school, like.
Yeah. I think this year would be the same. I think.
But last year I didn't have, okay? Last year my students were so good.
Yeah. The same thing.
So good, they were.
All the
they'll
students
till the
are very
last
nice.
Day.
Yeah.
Till the last day, they studied, they opened their books, they
Yeah.
brought their books, they
Yeah.
did their homework.
That's true. So it doesn't depend on whether it's physics or English. So it depends on the
attitude.
mentality, attitude of the student. So don't worry about it. Maybe next year would be better.
I hope so.
Yeah. You're welcome.ยังครับยังเตรียมสอบกันหรือว่าไงครับเนี่ยภาพไพมณีเต็มเลย เตรียมสอบกันหรือว่าอย่างไรครับ
ใช่ไงไม่เฟิร์สไปเอาไปทำมามีไอเทมเยอะมากเลยอ่ะบางเอาเบสใส่ใส่ไม่เอาของที่สุดตามใส่ใช่ใช่ทำไมเอาเบสเลยก็ตอนแรกดูมันต้องใส่เลยคุณสู้อ่ะไม่ต้องสาวไม่ควรเป็นโอ้โห
โทษครับ
อยากรู้ว่าเขาถูกก่อนที่ถ้ากูผิดปากมากกว่าเจ็บคอเลยเกี่ยวโบนเหรอดูเหมือนมึงอยากบอกกูว่าเลยว่าใช่แล้ว
เอากระสิจะมาเรียนห้องนี้ด้วยครับใช่แล้วคุณไม่เรียนภาษาอังกฤษกับไบอันอะไรของหรือว่าวิชาเขาง่ายคุณผ่านแน่นอน
เดี๋ยวผมดูอาจารย์สอนดีกว่า
ข้อมันเยอะมากเลยอ๋อมันแต่ไม่ได้ทำ4 ข้อ23 ข้อเฮ้ยเป็น6 ข้อสำหรับโมเดล 1อ่ะโมเดล 1คือข้อมันเยอะมากถ้าไม่ได้700ก็ต้องได้ต่ำกว่า5 ข้อเป็นไปไม่ได้มาช่วยได้ไหมฉันไม่ได้คุยผิดหมดเลย
ได้ยินว่ามาอะไรแค่ที่อยู่ในเป็นโทรศัพท์แล้ว
ใครสั่งในร้านให้มันขโมยเทมไม่ได้หรอกเราจะกินไอเทมเยอะมากแล้วคุณจะไม่ให้ใครนี่ไปถูกใครสั่งเลยใครสั่งว่าตัวฟังไอ้ที่นี่คือเจ้าของคนหน้าเหรอแค่พัดเซ็ตโอเซ็ต2004 XD35 ใครเลยที่เฮ้ยเดี๋ยวนะทำไมคิดดีเอาแล้วทำไมเขาใช้
โอ้ปี 2023 มาลายแคลรี่เขาไม่แก่ลงสักนิดเลยเขายังหน้าตึงๆอยู่เหมือนเดิมเลยผมว่าผมเห็นเขาตั้งแต่ผมอยู่ม.ต้นหรือม.อะไรไม่ใช่เหรอไม่ยอมแก่อะไรเลยทำได้ไงครับเนี่ยเดี๋ยวเราจะทำไงดีเกี่ยวกับเรื่องแลบเรานะครับ เขาจะให้ชดเชยวันพฤหัสป่ะประมาณ4 คาบนะเขานโยบายโรงเรียนเขาจะให้ทำแลบไม่ใช่ดิให้ชดเชย4 คาบในวันพฤหัสมั้งครับผมไม่รู้ว่าพฤหัสไหนแต่ว่าคงเราน่าจะจบทฤษฎีในวันนี้นะครับของบทที่6นะครับแล้วก็อีก4 ครั้งไว้ทำการทดลองเพื่อเก็บคะแนนฮะโอ้ไม่ใช่4 คาบผมไม่รู้เหมือนกันอาจจะเป็นพฤหัส2 ครั้งละ2 คาบอย่างเงี้ยครับมันอาจจะมีวิชาอื่นที่เขาต้องชดเชยได้บ้างมันจะมาฟิสิกส์อย่างเดียวคงไม่ได้ครับนะ
จะไปฟังเพลงของค็อกเทลอยู่ไกลใช่ปะ
อะไรครับ
ฟังกูเอาเดฟเอานิวแวน50%ใส่เลย
ยาแก้เจ็บคอเลย
อยากแก้ไอครับผมว่าผมไอน้อยลงแล้วนะน่าจะใกล้หายเรื่อยๆแล้วเดี๋ยวศิลวิทย์ตกใจอีกเหมือนคราวที่แล้วอยู่ดีผมก็พูดดังขึ้นมาครับมันคือลมไอออกมาครับมันก็เลยพูดเสียงดังแล้วโอเคWhere is that? My God. ไหนครับเพลงนี้ผมเห็นรุ่นพี่คุณกระเป๋ามันโน้ตเป็นยังไงอ๋อไม่มีโน้ตนะไม่มีคิดว่ามีโน้ตเขาบอกมาให้โน้ตอะไรด้วยอย่างเงี้ยรอเรือรอลิงซอโซ่อะไรอย่างเงี้ยครับโอเคมากโอเคlet's consider our class attendance. Oh, you send some letters, right? In the M604 live book. ว่างๆอยู่นะครับเซตไลน์กรุ๊ปของนั่นเลยวิชา IS ขึ้นมาครับเปิดแล้วก็เชิญเพื่อนเชิญผมเข้ามาไม่พิมพ์ไลน์มาแล้วคุณก็ไม่ทำมันไม่ก้าวหน้าครับโอเคไหมผมจะได้ถ่ายโอนข้อมูลก๊อปปี้ที่คุณพิมพ์ในไลน์กรุ๊ปของฟิสิกส์เอาไปใส่ในนั้นนะครับโอเคมากหรือคุณจะไม่เอาคะแนน IS ตกยกห้องเอาวะเอาครับติด0ยกห้องเลยวิชา IS คุณไม่เปิดไลน์กรุ๊ปมาเดี๋ยวมีใครบ้างทีทัศน์ไม่อยู่นะครับเอาเหมือนผมเลยเจ็บคอไอติดจับผมไปแล้วแน่นอนครับอริยวุฒิก็ไอด้วยเลยทันทีเลยครับทีทัศน์9แล้วก็ลาป่วยชยุทธพลเอาละไอเสมหะเหมือนกันเลยชยุทธพลอยู่ไหนเนี่ยแป๊บหนึ่งเอาพวกคนที่ลาก่อนคุณมาส่งกันวันนี้ผมก็ตั้งตัวไม่ทันแล้วครับถ้าส่งเมื่อวานนี้ได้อยู่สดุดี ไม่สบายตัวแล้วเป็นไข้แถวนี้นะครับสวัสดีไม่สบายตัวแล้วเป็นไข้ก็กมลสิทธิ์อ๋อตัวใหญ่นั่นไปสอบแอคที่ทางจังหวัดกมลสิทธิ์ไปด้วยนะครับคุณไปจังหวัดไหนเนี่ยกมลสิทธิ์อ่ะขอบคุณมากนะสำหรับนักรบนะครับต้องตั้งชื่อเป็นแบบว่า2 ห้องนะมีทั้ง2 ห้องนะครับห้องเดียวไม่ได้นะเพราะว่ามันต้องเปลี่ยนเป็น M605 ด้วยแล้วก็ประกาศเรียกเพื่อนเข้ามาทั้งหมดครับไปเรียกเพื่อนเข้ามาในไอ้นี่ให้หมดครับเขาเรียกว่า IS อ่ะเฮ้ยมันเท่าไหร่28 กับ 30ป่ะห้องนู้น30ห้องนี้ห้องนู้นเท่าไหร่มานะบวกกับ30เนี่ยต้อง58 คนนะเข้ามันไม่ได้ออกนี่หรอเนี่ยนะครับ
ว่าเล่นแบบนี้มันเล่นง่ายเล่นเลย
IS4 เหรอ IS6 ป่ะ Independent Study 6 อ่ะชื่อนะโอเคนะครับเข้ามาให้ครบทั้งหมดนะครับในนี้นะแล้วก็จะได้ถ่ายโอนข้อมูลไม่งั้นเดี๋ยวผมส่งข้อมูลในวันนี้หายหมดนะครับเดี๋ยวแชร์ใส่ที่ IS คุณไว้ก่อนเดี๋ยวมันหายนะครับเดี๋ยววันนี้ผมส่งผลอะไรการเรียนของวิชาฟิสิกส์เราพวกข้อมูลพวกนี้จะหายครับย้ายไปนู่นก่อนตอนนี้กูเข้าไปรวมมันลูกพ่อจะยาวเกินไปนะครับ
ถ่าย3